A Mass Spring System and Pendulum Lab by Newton's Balls.
In order to perform the mass spring system experiment, there are 4 steps you must take. First, you must set up the system by setting up a spring stand, attaching a spring to the ring stand, and attaching a weight to the spring. The second step is to identify all your known variables, which would be mass and the force of gravity. The third step is to find all the unknown variables, such as k, the spring coefficient, by using Hooke's law, the theoretical period, by using the formula, and the experimental period, by stretching out the spring and recording. The fourth step is to prove that the amplitude does not have an effect on the period. To accomplish this, you must vary the amplitude throughout several experiments. In order to conduct our experiment, we needed to find the spring coefficient k. We did this by using Hooke's law, which is the force of the spring is equal to the spring coefficient times x. We knew that the force of the spring was equal to the force of gravity because the weight stayed suspended in midair, and by recording how far the spring was stretched, x, we were able to find k. We found the period, t, by pulling the mass down and releasing it so then the mass spring system could oscillate. Then using a slow motion camera, we recorded how many seconds were in one cycle. By pulling the mass down at different lengths and seeing that the period was the same throughout all the experiments, we were able to conclude that the amplitude has no effect on the period.
Our margin of error can be attributed to human error because the spring stand shook due to our inability to perfectly stabilize it. The loss of energy due to heat, although minuscule, is a contributing factor to our margin of error as well. Our margin only exceeded 0.1 second at the most. Regardless of how large or small the amplitude A was, we found that the time it took for our mass spring system to complete one cycle remained similar. Whether it's at an amplitude of 0.008 meters or 0.112 meters, the period t remained relatively similar. With this data, we can conclude that the amount the spring is stretched doesn't affect how long it takes the system to complete a cycle.
A pendulum is a mass connected to a rod or rope that experiences simple harmonic motion as it swings back and forth, without friction. A pendulum's trajectory describes the arc of a circle with the length of the rope, L, being the radius of that circle. In this free body diagram, it shows that 2 forces act on the system. F equals mg pulls the mass straight down, and the force tension of the rod or rope pulls the mass upward. Notice that force tension is along the same line as mg cosine theta, so force tension equals mg cosine theta. When the angle is under 15 degrees, sine theta equals theta. So the restoring force, F restoring, equals negative sine theta mg. Similar to the mass spring equation, force spring equals negative kx.
What we need to do to make the pendulum is cut out a strand of fishing line and tie it onto the spring stand. Have 3 different masses for the different trials and a protractor to measure the angle where the pendulum starts on.
In trial 1, we tested 3 different lengths to see how it would affect the equation as a whole. The first length of the string was 0.167 meters, the second length was 0.296 meters, and the last length was the shortest at 0.147 meters. After going through a series of steps, starting from force spring equals negative kx, you'll find that t, the period, equals 2 pi square root of L length over 9.8, which is the only equation we used throughout this experiment. We found that the longer the length of the string, the larger the period was. The shortest length of string in part 3 of the first trial made the period shorter by 0.07 Hertz when compared to part 1, and shorter by 0.22 Hertz when compared to part 2. So the shorter the length of the string, the shorter the period as well. In the second trial, we wanted to test and see if mass had any effect on the equation as a whole, even though it's not included in the equation. In the first part, it was a mass of 0.05 kilograms, the second part was 0.2 kilograms, and the third part was 0.02 kilograms. The results of Trial 2 proved that mass does not affect the system. When every component was consistent except for mass, the outcome of the period, t, stayed constant between 0.87 and 0.84 Hz. No change was observed. In the third trial, we tested to see what would happen if the angle were to change above 15 degrees. The first part of it, we only did it at an angle of 10 degrees, and in the second part, we raised it to release at an angle of 20 degrees. Although a simple harmonic motion system should be changed when the angle is increased above 15 degrees, we found the system's results barely changed. T was only different by 0.02 Hz when compared to the angle below 15 degrees. So the angle does affect the system, but not by much in this circumstance. The reasons for the large margins of error between the theoretical and experimental periods are mostly due to human error when calculating the time or when releasing the object from rest. The average margin of error was 9.37%, with the highest being 13% and the lowest being 0%. All in all, these trials together prove the equation t equals 2 pi square root of L over 9.81, since the only variable that affected the system was the length of the string or rope the mass hung from, and the mass and the angle barely changed anything.